In the first part of this challenge problem, we're asked to develop an expression for the velocity profile between a stationary wedge and a moving belt. To do this, we need to assume that the velocity in the y and z are going to be 0. We're given that it's fully developed and the flow is of uniform pressure. We can then write the continuity equation and cancel out given our assumptions, and we're left with du dx is equal to 0. We will use this when we write the full Navier-Stokes equation, which is right here. So the full Navier-Stokes equation for the x momentum is given here. We can cancel out all these using these assumptions, and we're left with this expression. When we write it in terms, we can solve for g of x is sine of theta times g, and solving for or integrating twice gives us an expression for u. And when we plug into our two known values for u, which is it's going to be 0 at y is equal to 0, and it's going to be negative VB at y is equal to h. We can solve for C1 and C2, and then plugging in what we got for C1 and C2, we got this expression for C1, and C2 is equal to 0. Back into our expression for u, we are given this, and this is the expression for the velocity profile in the y direction for our flow. In the second part of this problem, we're asked to find what an expression for the velocity profile is if there is no net flow. And we can do this by integrating from 0 to h of u, our expression that we previously found, and setting that equal to 0. And so when we take the integral and solve everything, we can get VB on one side. And solving for VB and simplifying, we get this expression. This is the velocity of the belt required to have 0 net flow in our fluid. In the last part of our problem, we're asked to sketch the velocity profile. And so we can do this by plugging what we found for VB into our expression for u. And so simplifying the expression, we're given this. And so this, the y divided by 3 minus y squared divided by 2, that's going to be the shape of our profile. And then we know that at the stationary wedge, the velocity is going to be equal to 0. And that at this point, at the belt, our velocity is going to be equal to this. And this is going to be the shape in between the two. So yeah, this is the solution to part C.